Hi, everyone. What we're going to be doing today is we're going to be solving trig equations. And many of these problems will refer to the principal values limiting our domain. So I just wanted to give you a little reminder about the principal values. Um, Recall that with the principal values, we have basically one quadrant for a positive value and one quadrant for a negative value that, like if you put this in your calculator would default to that answer. So we know sine is negative here, sine is positive here. Cosine is positive here, cosine is negative here. Tangent is negative here, and it's positive here. So just remember those values, the principal values, as we move through the next batch of problems. So if you look at the first example, what we're doing is we're asked to solve this equation for the principal values of x and express it in degrees. Now, what I want you to think about is when we're solving an equation like this, all of the rules for solving will apply. So, for example, in this problem, we're factoring a trinomial, right? We have a trinomial that's set equal to 0. We're going to have to factor that. Well, sometimes looking at this can be confusing. So I'm going to replace these two values with just an x, just to give you an example. And you're not going to do this every time. I'm only doing it because it's the first one. So if I gave you this equation and asked you to solve it, I would imagine you would use a ratio method and say, well, I have to factor this. So 2 times negative 1 is negative 2. And I know that 2 times negative 1 equals negative 2. 2 combined with negative 1 equals positive 1. And then, of course, it's the ratio method, so we have to put the lead coefficient in front and reduce. Well, if this wasn't the equation, if it was just like this with x's, what we would have is x plus 1 times 2x minus 1 equals 0. But this does have sine of x. So instead of writing this, again, going back to this is really what we were supposed to be solving. Our equation would actually be sine of x plus 1 times 2 times the sine of x minus 1 equals 0. And I hope you see the connection between these two. X plus 1, sine of x plus 1. 2x minus 1, 2 sine of x minus 1. And what we'll do is we will solve these using the zero product property. So we will take sine of x plus 1 and set it equal to 0 and solve. So we get sine of x equals negative 1. And now that's not the answer, but that's going to get us to the answer. And for the second one, we would set this equal to 0. You would add the 1 and divide by 2. I'm going to save us a little bit of writing here. So we wind up with the sine of x equals 1/2. Now, we have to think about our unit circle. We have to think about our principal values. So when we look at our principal values, we are restricted to this domain. So where is the sine of x equal to negative 1? Well, I hope you know from your unit circle, x would have to be a negative 90-degree angle. Okay? And also, we would have to find where the sine of x equals 1/2. Again, sine is height. So what angle has a height of 1/2 on our unit circle? And hopefully you remember that that would be a 30-degree angle. So those would be the two answers to this. Now, if we weren't limited, okay, if we weren't limited to the principal values, like this next question is asking, now we can use the entire unit circle. And notice it's from 0 to 360, so we want our angles to all be positive. We want all positive degrees. So thinking about it, we would still have that 30-degree angle, so x would equal 30 degrees, but I'm going to use a different color. Sine is also 1/2 over here. So when we have a 30-degree reference angle, that would be a 150-degree angle. And again, because we're between 0 and 360, we would have to go around the circle this way, and instead of saying negative 90, we would give our answer as 270 degrees. So by opening the domain up to the whole circle, we had to rename our negative 90 to be 270, and we also got another angle whose height was 1/2. And then the last one, the last way that we can kind of change our domain for this problem is if it was a set of all real numbers. And you might recall this from a long time ago, but that's when you give all of the angles that could be coterminal with the angles that we just found. So x would be the 30-degree angle plus or minus 360k. In other words, you add as many full circles or subtract as many full circles as you want to 30 degrees, you will still be in the same spot. So, of course, the same thing. 150 plus or minus 360k and 270 plus or minus 360k. Okay, so you have to be very careful with the domain that you're given so that you're giving the correct answer and not too much of an answer and, not leaving anything out. Okay, so let's look at this next problem. The next problem, I want you to look very carefully. Sine of x times cosine of x minus 1/2 cosine of x for all principal values. And again, we're going to express it in degrees. Well, let's think about how we would solve this. What I notice is we have one term here, and we have the other term here. And what do they have in common? Well, their GCF is the cosine of x. So we are going to factor out the cosine of x. That will leave us with the sine of x minus 1/2. And it's already set equal to 0. And once again, we can use the zero product property because we have one term times, or one value times another value. So we can say that the cosine of x equals 0. And the sine of x minus 1/2 equals 0. So I'm just going to add that 1/2 to the other side. So sine of x equals 1/2. So we have to think about this very carefully. Cosine of x, again, it said principal values. So the principal values for that are from 0 to 180. So the solution here, where is the cosine of x 0? Well, it's right here at 90 degrees. So x equals 90 degrees. For the second one, we have a different, the principal values are different. It's from negative 90 to positive 90. We just did this in the previous problem. So x equals 30 degrees. It would be right here at 30 degrees. So we had two different answers for that one. And one used, they used different principal values because they're not the same for sine and cosine. Okay, second question here. Building on that, it says express the answer if the domain was from 0 to 360. So now if you can think, okay, obviously the 90 degrees is still going to be there for cosine. Whoops, forgot my x equals. But where else on the whole entire unit circle is cosine 0? Well, it's at 90, but it's also at 270 because remember, cosine is the x value. Okay, so we have two answers now. And just like the previous problem, we had from this equation, we were given the 30-degree angle, but we also know there's another angle over here at 150 degrees whose sine is also 1/2. Okay, so hopefully that makes sense. And once again, we're told, okay, now that you've used been restricted to the principal values, and then we opened it up to the unit circle. Now, what if you could give all real numbers, a set of all real numbers for your domain? It would be all of these values plus or minus 360. So 30 degrees plus or minus 360k. Sorry, I forgot the k. I like to put them in order. So 90 degrees plus or minus 360k. 150 degrees plus or minus 360k. And of course, 270 plus or minus 360k. Okay? So let's see what we have on the next page. Okay, we have another example. And this time, it's giving you the domain in terms of radians, which means you're going to give your answer in terms of radians. So you pretty much follow how the domain is given to you, and then that's what you're going to do. That's how you're going to give your answer. What I notice in this problem is it looks like I have sine squared, sine, and a constant, and then I have cosine squared here. So it's going to be a little hard to factor if we have sine and cosine squared in our equation. So what I'm going to do is I'm going to use our identities, and I'm going to replace cosine squared with 1 minus sine squared of theta. And I'm going to bring everything else down unchanged. The benefit of that is that now we have everything in terms of sine. So now we can subtract or add everything to one side, set it equal to 0, and solve. So we're going to add this to this side. Of course, you're combining like terms. We're going to subtract 1. That's kind of nice because those cancel out. This is all gone. And we now have 2 sine squared of theta. I know I made my x's into thetas. Minus sine of theta equals 0. And this is a pretty simple one to solve because once again, in both terms, we have sine of theta. So we can factor out that GCF. We are left with 2 times the sine of theta minus 1 equals 0. And here we go. I'm going to go right up here. Need a little more room. So we get sine of theta equals 0. And sine of theta equals, add 1, divide by 2, equals 1/2. So that one keeps coming up, right? But recall, we have to give our answers in terms of radians. So where is the sine of theta 0? Well, it's at 0 pi, and it's also at pi. Where is the sine of theta at 1/2? Now, I know we just did it in terms of degrees, and it was 30 degrees. But in terms of radians, hopefully you remember that that is pi over 6. And 150 degrees is 5 pi over 6. Okay, so that gave us basically the whole unit circle right here. Going a little backwards on this one because now we're restricting the domain where we say we'll express it if we were just working with the principal values. So we have to remember that only the answers that fall between negative pi over 2 and pi over 2 will be our answers, including both of those values. So 0 pi would be right here. So that's certainly one of our answers. 0, or you could put 0 pi, whatever you're comfortable with. Pi is over here. That's outside of our domain. Pi over 6 is right here. So that certainly works. 5 pi over 6 is also in the second quadrant, outside of our domain, so we ditch it. Okay? And the last one, it says, now express if the domain was the set of all real numbers. Well, again, we are in terms of pi. So we're going to give our answers in radians. So we will say x equals 0 plus 2 pi k. I'm going back up to these, by the way. These are the ones we're using right now. So pi plus or minus 2 pi k, and you might have noticed there's an easier way to do these two, but we'll just leave it. Pi over 6 plus or minus 2 pi k, and then 5 pi over 6 plus or minus 2 pi k. So hopefully you're getting the hang of this. What I'd like for you to do is I'd like for you to pause the video, go ahead and work on the next problem, and then start the video up again and see if you get the same thing that I get. What I'd like to point out to you again is now we have cosine squared, cosine, negative cosine is our linear term, and 1. and then we have sine squared. So my hint is that you're going to want to do something with the sine squared of x. Okay, so pause the video, do the work, and then we'll see if our answers are the same. All right, let's see how you did. Okay, so hopefully you replace sine squared of x with 1 minus cosine squared of x, move things over, factored, which would have gotten you to here. And then, of course, using your unit circle, we would have gotten these 4 answers. Then we restricted the circle to really only focusing on the principles at values. So anything from 0 to 180, which eliminated 3 pi over 2 and 5 pi over 3. And then we had to express the answer if the domain was all real numbers. And I have a couple things here. So pi over 2 and 3 pi over 2, I didn't know if you noticed this, but they're 180 degrees apart or pi apart. So if you didn't want to do plus 2 pi k for each of these, you could say pi over 2 plus pi k, because if you add a pi, you'll be here. If you add another pi, you'll be here. If you add another pi, you'll be here. So I'm not really too picky about that, but just wanted to point that out. And of course, the other 2 angles with, adding full circles. So have a great day, everybody.